Quantum computing promises to revolutionize technology in ways we're only beginning to imagine. Unlike traditional computers, quantum machines harness the strange power of quantum physics to solve problems exponentially faster, potentially transforming everything from medicine and cryptography to artificial intelligence. But what exactly is quantum computing, and how close are we to making it a reality? In this video, we'll explore the basics of this cutting-edge technology, the breakthroughs driving it forward, and what it could mean for the future of tech in our world. Get ready to step into the quantum era. Today, we will talk about quantum computing, what it means for the future of tech. So before we get started, make sure to hit that like button, also subscribe to my channel. Understanding the basics. What is quantum computing? At its most basic level, quantum computing harnesses the unusual behaviors of particles at the quantum scale. Unlike classical computers, which use bits as the smallest unit of data, each bit being a 0 or a 1, quantum computers use quantum bits or qubits. What sets qubits apart is their ability to exist in multiple states simultaneously thanks to a property called superposition. Imagine flipping a coin. While it's in the air, it's both heads and tails at the same time. Qubits act somewhat like that coin in midair, holding multiple possibilities simultaneously until measured. This means a quantum computer can explore many potential solutions to a problem all at once, rather than one at a time like a classical computer. Another key feature is entanglement, a phenomenon Albert Einstein famously called spooky action at a distance. When qubits become entangled, the state of one qubit instantly influences the state of another, regardless of the distance separating them. This creates an extraordinary link that classical bits simply cannot replicate. Together, superposition and entanglement give quantum computers a computational edge, enabling them to process vast amounts of data in ways unimaginable with traditional technology. How quantum computers work, a new approach to problem solving. Quantum computing operates fundamentally differently from classical computing. Classical computers process instructions sequentially or in parallel using transistors that switch on or off, representing ones and zeros. Quantum computers manipulate qubits using quantum gates that perform complex operations on probabilities instead of definite states. Building a quantum computer involves maintaining delicate quantum states, which is a significant engineering challenge. Qubits must remain coherent, that is, preserve their quantum state, long enough to complete calculations. Unfortunately, quantum states are fragile and susceptible to disturbances from their environment. A challenge known researchers have developed various physical implementations for qubits, including superconducting circuits cooled to near absolute zero temperatures, trapped ions suspended in electromagnetic fields, and exotic topological states that are more resistant to errors. Each approach aims to increase the number of qubits and their stability to eventually create machines capable of practical problem solving. Quantum algorithms, like Shor's algorithm for factoring large numbers or Grover's search algorithm, are designed to exploit the properties of qubits to solve specific problems much faster than classical algorithms. The promise of quantum computing, transforming industries and research. Quantum computing is poised to redefine multiple fields by enabling breakthroughs impossible with classical technology. One of the most widely discussed applications is cryptography. Current internet security relies heavily on encryption methods based on the difficulty of factoring large numbers. Quantum computers running Shor's algorithm could break these encryptions rapidly, rendering today's security measures obsolete. This reality drives urgent research into post-quantum cryptography, which aims to develop new security protocols resistant to quantum attacks. Beyond cryptography, quantum computing has enormous potential in chemistry and materials science. Simulating molecules and chemical reactions accurately is incredibly resource-intensive on classical computers. Quantum computers can model these processes naturally, potentially leading to revolutionary advancements in drug discovery, new materials, and energy storage. This capability could accelerate the development of medicines tailored to individual genetics or new efficient catalysts for industrial processes. Finance is another sector that could be transformed. Quantum algorithms can optimize portfolios, simulate complex market dynamics, and price derivatives with a level of precision unattainable with classical methods. These improvements could fundamentally change risk assessment and investment strategies, creating new opportunities for financial innovation. In climate science, quantum simulations might enhance our understanding of atmospheric chemistry and global systems, improving climate models and guiding efforts to mitigate environmental challenges. Overcoming the challenges. Why quantum computing isn't here yet? Despite its promise, quantum computing remains a work in progress, facing significant technical and theoretical obstacles. One of the largest challenges is error correction. Qubits are prone to errors due to decoherence and operational imperfections. Unlike classical bits, which can be easily checked and corrected, quantum states collapse when measured, making error detection more complicated. Developing quantum error correction codes and fault-tolerant architectures is essential to scaling up quantum computers. This remains an active area of research, requiring innovations in both hardware and software. Another challenge is developing algorithms that leverage quantum speedups for practical problems. While some algorithms show clear advantages, many real-world problems lack efficient quantum solutions at this stage. The field continues to grow, but it will take time before quantum computing can address a broad range of challenges effectively. Accessibility and infrastructure also limit quantum computing's current reach. These machines require extremely specialized environments with ultra-cold temperatures and vibration-free settings, meaning they are currently confined to specialized labs and cloud platforms. Ethical and security implications of quantum computing. As with any powerful technology, quantum computing brings important ethical and security considerations. The potential to break encryption threatens global cybersecurity and privacy. Governments, corporations, and individuals must prepare for a future where current security protocols are no longer safe. This risk prompts a race to develop quantum-resistant encryption standards and to carefully regulate access to quantum technology. Additionally, the unequal distribution of quantum capabilities could widen global inequalities and technological divides. Transparency, ethical guidelines, and international cooperation will be critical to ensuring that quantum computing benefits society broadly without compromising security or fairness. What do you think of our video? Let me know in the comment section below. Before you go, please hit the like button and subscribe to my channel. Thanks for watching.